Welcome back to Domain 2 of the Security Plus Exam Cram Series 2024 edition, and here in Section 2.3 we'll be focused on vulnerabilities, from apps and operating systems to hardware and virtual. We'll dig into web, mobile, and cloud vulnerabilities and examine cryptographic and zero-day considerations. Lots to cover, so let's get to it. Welcome back to the Security Plus Exam Cram Series 2024 edition, and in our continuing coverage of Domain 2, we'll dive into Section 2.3 of the SY0-701 exam, focusing on vulnerabilities. More specifically, the syllabus asks us to explain various types of vulnerabilities. We'll examine vulnerabilities across a number of categories, including application, operating system, web-based vulnerabilities, hardware, virtualization, cloud-specific, a much bigger topic than that single line on the syllabus indicates, supply chain, cryptographic, and misconfiguration, mobile device, and finally, zero-day vulnerabilities. But before we dive into all this material, there are 4 terms you must know before we begin. These represent foundational knowledge that will help you to understand everything we're about to talk about, so I'll cover those right now. First, we have vulnerability, which is a weakness in a system, application, or infrastructure that can be exploited to gain unauthorized access or to cause damage. It's the flaw or gap in security that could be taken advantage of. Then we have a threat, which is a potential event that could exploit a vulnerability and cause harm. It's the possibility of something bad happening. An exploit is a specific method or tool used to take advantage of a vulnerability. It's like the recipe for hacking that leverages the system's weakness. And finally, the attack, which is the actual attempt to exploit a vulnerability to achieve the malicious goal. So let's look at how these relate to one another in the context of a potential security breach. So a vulnerability exists in a system. A bad actor identifies this threat and sees an opportunity. The attacker then develops or uses an existing exploit to take advantage of the vulnerability. And if successful, this becomes a full-blown attack, causing harm to the system or its data. Let me give you a simple analogy to tie all these together that you may find helpful. So imagine a house with a weak lock. That's the vulnerability. We have a burglar, who is the threat, who sees this and uses a crowbar, the exploit, to break in, the attack. So by understanding these terms and their relationship, you should be able to better identify and address security risks in your own systems. But for exam day, it will help you understand what's being asked of you in those exam questions. So let's get into vulnerabilities, beginning with buffer overflows, which are attacks attackers use to exploit poorly written software. A buffer overflow exists when a developer writes code that doesn't validate user input to ensure it doesn't allow input that is too large for its memory space. So when this occurs or is exploited, code or related data can overflow the memory buffer. We prevent this with input validation, and we can identify this with appropriate software testing. Maliciously inserting information into memory is known as memory injection, and this is the primary goal of a buffer overflow attack. One version of the buffer overflow is the integer overflow, which involves putting too much information into too small of a space that has been set aside for numbers. It's a type of arithmetic overflow error when the result of an integer operation does not fit within the allocated memory space. Instead of an error handled in the program, it usually causes the result to be unexpected, and this often leads to buffer overflows and is generally ranked as one of the most dangerous software errors. Your error messages may include overflow or arithmetic overflow. Your countermeasures in this case are secure coding practices, where we make sure we're validating the size of our data. This is generally handled through appropriate typing of our variables. So we could use larger variable types like long in Java or long integer in C, both of which accommodate 64 bits. Next, we have race conditions, which is a condition where the system's behavior is dependent on the sequence or timing of other uncontrollable events. So the time of check is the moment a system verifies access permissions or other security controls. And the time of use is the moment when the system accesses the resources or otherwise uses those granted permissions. This creates a vulnerability to a time of check, time of use exploit. It's a timing vulnerability that occurs when the program checks access permissions too far in advance of a resource request. And when use is attempted, access is no longer there. Next, we have malicious updates, which is where an attacker attempts to deploy a fake patch that is designed to compromise the security of an application or an operating system. Software publishers can protect against this threat with code signing, and if systems only accept signed updates, the threat is effectively mitigated. When it comes to operating systems, we have several potential OS-based vulnerabilities. Default settings, like default passwords or settings that are insecure out of the box, or even unneeded apps or services, all of which become potential paths for attackers. I will say many operating systems today aim for secure defaults. I know that's true with Mac and Windows in particular, but you still need to establish your intended starting point, what we'd call your configuration baseline. Which brings us to configurations or misconfigurations, as configurations are often intentional, but they may not be secure, and that's where secure configuration baselines come in handy. We establish a baseline configuration, a starting point that we know covers our needs in production without unwanted apps and services, and then we can use a vulnerability scanner to ensure that we don't have any holes in our configuration. Any security holes, that is. Then we have privilege escalation, vulnerabilities that allow attackers to gain higher privileges on a system than they should have, allowing access to sensitive data or to install malware. The fix here is we require authentication to elevate, so that's user access control in Windows or sudo on Linux and Unix platforms. Zero-day are a category of vulnerabilities that are unknown to the software or hardware vendor and very dangerous because there is no patch available to fix them. Defense in depth with AI and next-gen capabilities that we see in XDR, extended detection and response, intrusion detection and prevention systems, as well as CASB, Cloud Access Security Brokers, can offer layers of defense to help identify potentially malicious behaviors and stop them before they become a full-blown attack. Bottom line, an operating system has many features, but the zero-day can target other apps, systems, data, and infrastructure. And in those many OS features, we have to remember the more features we enable, the greater our attack surface. That's why for operating systems on the whole, we want to establish that secure baseline that gives us the configuration with functionality that we need and nothing that we don't. Next up, we have vulnerabilities compromised through web-based threats, and these are exploited due to weakness in improper input handling. The first vulnerability we're going to examine is used to compromise front-end web apps and their back-end databases. Amongst the most common, we have the SQL injection attack, which use unexpected input to a web application to gain unauthorized access to an underlying database. SQL injections are not new, and they can generally be prevented through good and secure coding practices. Your common countermeasures include input validation first and foremost, using stored procedures, pre-compiled code rather than SQL queries, SQL statements, and to limit account privileges. And another in the web-based category you should know for the exam is a type of injection that uses malicious scripts called the cross-site scripting attack. It's a type of injection in which malicious scripts are injected into an otherwise benign and trusted website, often through an input field. It occurs when an attacker uses a web application to send malicious code to a different end user. It occurs when web apps contain what's called reflected input. As with SQL injection, a good defense is input validation and filtering to catch malicious scripts, and validating data length and data type. Now, the cross-site scripting attack exploits client-side trust, but the server plays a role as well. Let me explain through an analogy, just a simple example. So here's something you might find helpful. Let's take a bakery accidentally mixing broken glass into a batch of cookies. That's the server-side vulnerability. People buying those cookies from the bakery would trust that bakery, but if someone eats those cookies, they're going to get hurt. That's the client-side execution. The bakery, the server in this case, is responsible for ensuring safe ingredient, validated user input. Validating those ingredients, ensuring those cookies are safe before serving them to their customer, just as the server should validate the input on that web page before serving it to the trusting client. An oversimplification, but I hope that helps in digesting the cross-site scripting attack. And next we have the hardware category, and hardware vulnerabilities require attention in the design phase because some of your compensating controls are hardware-based. Firmware is a commonly attacked vulnerability, and firmware attacks can occur through the update process or one-off malicious downloads that impact the boot process. Good prevention here is a trusted platform module or TPM on the motherboard to facilitate a secure boot process, and we'll dig into the TPM elsewhere in this series. Next we have end of life, so aging equipment that has some usable lifespan left. You should have a timeline of replacement in advance of production deployment, because replacing that hardware is going to require both budget and time and effort for the project to perform the replacement, to migrate applications or data that reside on that hardware over to the new hardware. And then we have legacy. Now the definition of legacy is a bit less clear and can take on several meanings, but for the exam, legacy is used to describe hardware, software, or devices that are unsupported. Next, we have the virtualization category. So server virtualization is the process of dividing a physical server into multiple unique and isolated virtual servers by means of a software application, the hypervisor. So virtual servers are commonly called VMs. Hypervisors would include things like VMware ESX or ESXi, or Microsoft's Hyper-V. The related concepts around this indicate server virtualization is the focus in this portion of the exam, in this particular line item. And that's because the vulnerability cited is VM escape, where an attacker gains access to a VM, then attacks either the host machine that holds all the VMs, the hypervisor, or any of the other VMs. Proactive measures here would include ensuring patches for hypervisor and VMs are always up to date, and guest privileges are low. Server-level redundancy is a good idea, and host-based intrusion detection and prevention are also effective. The other vulnerability cited in this category is resource reuse, which happens when cloud providers take hardware resources originally assigned to one customer and reuse them with another. This creates a risk of data remnants due to incomplete erasure. If the storage isn't securely erased, there may be some recovery of data possible through forensic means. So to avoid this, you want to make sure that you encrypt your sensitive data so it cannot be recovered by the next customer through forensic techniques. In a VM, that's going to be very simple, full disk encryption. So that's going to be BitLocker on the Windows platform, that's going to be dmcrypt on the Linux platform. Next up is the cloud category, which takes on heightened relevance here in 2024. I actually have 11 examples of vulnerabilities I'm going to touch on in this category for you, all coming from an authoritative list and a very credible source. So the primary vulnerability in the cloud is that it is an internet-based model. Organizations could be at risk if the CSP's public-facing infrastructure comes under attack, number one. Any attack on your CSP or cloud vendor may be unrelated to you as an organization. Threat actors may be targeting the CSP or another tenant of the CSP even. And technically, risk could even come from other tenants as well. But in this scenario, customers may be collateral damage of an attack on the CSP in some circumstances. I want to take you through a list of cloud-specific risks from the Cloud Security Alliance. They detail the top cloud-specific security threats in their list entitled the CSA Egregious 11. There's a word you don't hear every day. Egregious means shockingly bad, in case you're not familiar. So I'll list the 11 here. Some perhaps you've seen before, many I suspect you've never heard of, and we'll dig into each of the 11 in detail one by one. First, we have data breaches, which is the loss of sensitive data, personally identifiable information, protected health info, intellectual property, sensitive data due to security breach. And that's data loss. Now, if we hear data leak, that refers to unintentional loss or oversharing of data. So keep data leak and data breach separate in your mind for exam day. Misconfiguration and inadequate change control. So software can offer the most secure configuration options, but if it's not properly set up, then the resulting system is going to have security issues. We remediate this risk, we prevent impact through change in configuration management. Lack of cloud security architecture and strategy. So as organizations migrate to the cloud, some overlook security or fail to consider their obligations in the shared responsibility model. You need to know who is responsible for security at each layer in the cloud, because sometimes it's you, and sometimes the cloud service provider will provide a feature for you to configure to make that feature secure, but you're responsible for configuration. And that's often due to the fact that every customer's needs are different, and you need to configure it to tailor the feature to your environment. Then there's insufficient identity, credential access, and key management. The public cloud offers benefits over legacy on-premises environments, but it also brings additional complexities, often in the form of new ways to configure familiar capabilities. Two great examples are identity and access management and secret and key management, which are going to be very different in the cloud versus on-premises. On the whole, identity and access management, encryption, key management, all of it tend to be greater versus what we see on premises, but new ways to implement these familiar features, so there's going to be something of a learning curve. Next, we have account hijacking, which is credential theft, abuse, and/or elevation to carry out an attack. Phishing is going to be the most common approach here, statistically speaking. Insider threat. So the vulnerability here are disgruntled employees, employee mistakes, and unintentional oversharing. So notice the threat is both due to intentional damage and unintentional damage. So job rotation and privileged access management will help us deal with the intentional, and auditing and security training can help us to identify the unintentional. And we have insecure interfaces and APIs, so customers failing to secure access to systems gated by APIs, web consoles, and other cloud interfaces. Controls include multi-factor authentication, role-based access control, or key-based API access, to name a few. A weak control plane, so weaknesses in the elements of a cloud system that enable cloud environment configuration and management is what we're talking about here. The web console, the CLIs and APIs that are all available to facilitate management and automation. You can mitigate these vulnerabilities by and large by following the CSP's advice. Your big CSPs, the Amazons, Microsofts, Googles, all provide reference architectures to ensure customers secure and isolate their dev, test, and prod environments, as well as their data. They all provide a well-architected framework, a cloud adoption framework, and more recently, a zero-trust adoption framework. So for insider threat, I gave you some options for minimizing that threat, but I want to show you some protections that are offered by CSPs in terms of tools or services in the cloud that allow us to proactively monitor for not only real insider threats, but the potential of insider threat. And again, the exam is vendor agnostic, so this is just an example for context. The capabilities are going to vary by CSP. I'm going to quickly browse to compliance.microsoft.com. This is Microsoft's Purview compliance portal, where we can configure a variety of features that help us with data in particular. And I'm going to scroll down in their solutions menu here, and you'll see they have one called Insider Risk Management. And it comes complete with features beginning with guided configuration. So you see here they give me the top actions to help getting us up and running. And then once we have the feature configured, so it's monitoring for those user actions, you see they have an alert portal here, so we can see any potential alerts that have been flagged. We can create cases so we can investigate and gather all the evidence. One would imagine that's generally for intentional insider risk, so the disgruntled employee category. We can configure policies here that will go out and scan daily user activity. They're tracking users, reports. You can even see here a forensic evidence tab. which is an investigative tool for viewing captured user activity. And this insider risk feature even has notice templates so we can standardize our communication, and some adaptive protection, which is going to involve some intelligence. Words like adaptive and intelligent usually tip us off that the feature involves AI and machine learning or some other advanced functionality. Continuing down the list, we have metastructure and applistructure failures. So vulnerabilities in the operational capabilities that CSPs make available, like APIs for accessing various cloud services. The danger here is if the CSP has inadequately secured these interfaces, any resulting solutions built on top of those services will inherit these weaknesses. We should address those terms metastructure and applistructure. So metastructure are the protocols and mechanisms that provide the interface between the cloud layers, enabling management and configuration. Applistructure are applications deployed in the cloud and the underlying application services used to build them. An example would be in platform as a service features like message queues or functions that drive automation when triggered, or messaging services of various sorts, where the CSP is providing a great deal of functionality that we can leverage through simple deployment. So who would be responsible in a situation like that? Well, responsibility in this case would rely with the cloud service providers. Customers need to verify the CSP has implemented their own secure software development lifecycle to ensure the service is adequately secure. Which means you may want to go to their portal and download a SOC 2 Type 2 audit and make sure that the service has been audited by a third party and it is adequately secure for your purposes as a customer. And that's the takeaway I want you to focus on for the exam. Don't worry about memorizing metastructure and applistructure. Those terms aren't coming up on this exam. Next, we have limited cloud usage visibility. This refers to when organizations experience a significant reduction in visibility over their information technology stack. This is because in some models, the CSP owns the stack. So whether or not this is truly a vulnerability comes down to understanding your responsibility in the shared responsibility model. And if there is some bit of information that you need to know that the CSP isn't showing you in the built-in reporting. And finally, we have abuse and nefarious use of cloud services. While the low cost and high scale of compute in the cloud is an advantage to enterprises, it's also an opportunity for attackers to execute disruptive attacks at scale. Because multiple customers share infrastructure, it makes executing distributed denial of service and phishing attacks easier, but more importantly, it makes it less expensive for bad actors to acquire high-scale compute for a low cost so they can disrupt organizations anywhere. So CSPs have to implement mitigating security controls for these sorts of risks. And the big three are all going to have some sort of built-in DDoS protection and potentially an optional premium tier of some sort you can buy to allow for enhanced configuration. So just understanding these vulnerabilities and how the attack surface changes is half the battle. Now the question is, how do we deal with these? And there are several approaches to risk mitigation in cloud environments. Many are just common sense. It begins with selecting a qualified CSP, making sure we have a CSP with the infrastructure and operations to support our needs and the security in place for the areas where they are responsible. The next step is designing and architecting with security in mind. Security should be considered at every step, starting with design. We call that DevSecOps. The next risk mitigation tool is encryption, and data should be encrypted both at rest and in transit. Storage and database encryption at rest, TLS and VPN in transit. And finally, ongoing monitoring and management to maintain security posture. Your major CSPs provide the ability to manage and monitor configuration security and to monitor changes to cloud services as well as to track usage. And cloud service providers do offer some help here. So again, just for context, I want to show you an example of how a cloud service provider gives you services and support for ongoing monitoring and maintenance of your security posture in the cloud. As an example, I'm going to show you Microsoft Defender for Cloud, which is a monitoring feature that allows us to monitor our cloud security posture as well as some workload-specific monitoring. But for purposes of this discussion, I'll just go to the Microsoft Defender for Cloud portal, and I'll come down here under Cloud Security and click on Security Posture. And what you'll see here is they even give us a score. They gamify it, so to speak. And that gamification is important because it quantifies my current position. So if I see that score go up or down, I know if I am improving or regressing. When I see the unhealthy resource count go up or down, I know which direction my security posture is headed. So let's look at the recommendations here, and they're going to give me a list. And in this particular tool for Defender for Cloud, they actually prioritize based on the impact and the ease of effort. That is to say, they're going to put the big wins and the quick wins up to the top of the list. And I see some common sense recommendations here. I should enable disk encryption on these VMs. I should configure secure communications on this server. And here's another common sense one. Web applications should only be accessible over HTTPS. Of course it should. Let's click on that recommendation and see what they give us under the hood. And so here I see they describe the deviation from best practices, and they even give me recommended actions. And in this case, they've gone a step further and they give me a quick fix. And they mention that after we fix it, it can take up to 30 minutes until this moves into the healthy category. But if I click on fix here, we notice we have just push button remediation. So there's a lot of cloud security posture management support for us in this tool, and similar tools on other cloud platforms as well. And they go beyond that in this particular tool. We even see workload protections, which would give us some features specific to PaaS services, for example, like databases and web applications. And they even have some regulatory compliance monitoring they can help us with. But bottom line, when it comes to ongoing monitoring and maintenance of your security posture, it behooves these cloud service providers to ensure you are successful so you continue to be a subscriber. So they give you tools to make that an easier task, generally speaking. Let's move on to the supply chain category. So sophisticated attackers may attempt to indirectly interfere with an organization's business through their supply chain. Attackers might gain access to hardware devices at the manufacturer or while in transit from the manufacturer to the end user, to the company. They may install backdoors or other malware for device control. They may also target software providers, inserting vulnerabilities into software before it's released. Attackers may compromise managed service providers to gain access to their network and, by association, the customers they service. So the vulnerabilities, as you can imagine, vary widely based on the type of vendor in the supply chain we're working with. So good prevention here is effective vendor management practices that uncover service provider security posture and practices to reduce risk, to ensure that we are not inheriting vulnerabilities that impose an unacceptable level of risk on our business. Next up, we have cryptographic vulnerabilities. These are the weaknesses or flaws in a cryptographic system that can be exploited to compromise system security. This is another big topic we could spend hours on. I'm going to give you a few examples here to give you some context of a range of areas of concern so you have some perspective for the exam. So examples like weak encryption, improper key management, inadequate randomness and authentication, key lifetimes, public key length, symmetric key length, the strength of our implementation. So in the area of cryptography, vulnerabilities like these can lead to severe consequences like exposure of our sensitive data, unauthorized system access, and other security breaches. Let's step through these examples one by one to give you some perspective, starting with weak encryption. So using an encryption algorithm that's no longer considered secure, for example, like DES or RSA with a small key size, which can make it easier for an attacker to decrypt information. We want to make sure we select algorithms that are well suited to our use case, widely accepted as secure, make sure we pick an adequate key size before we move into implementation. Improper key management, so failing to protect access to encryption keys adequately can compromise the sensitive information they protect. Keys should be stored in an access-restricted store or vault. Inadequate randomness. Some cryptographic algorithms, such as generating session keys, require a source of random numbers. And all of cryptography relies on randomness, on entropy. So in a situation where we need to provide source random values, we'd want to use a true random number generator, not a pseudo-random number generator, which can weaken our encryption. We're minimizing predictability. Next, we have inadequate authentication. So failing to authenticate parties properly in a cryptographic exchange can lead to man-in-the-middle attacks where an attacker intercepts and alters communications. Unauthenticated or even anonymous access is a big no-no when we think about security. Key lifetimes. The length of the time a key is used for encryption can affect the security of the cryptographic system. The longer that key is around, the more likely it is exposed to some compromise. So for example, client and server certificates should typically have a lifespan of no more than approximately 1 year. In fact, last I looked, I believe the recommended lifespan of an X.509 certificate is somewhere around 395 days as an industry standard. We have public key length, so given a key of the same length, public key cryptography, also known as asymmetric cryptography, is generally more vulnerable to attacks than symmetric key cryptography. So, for example, it's recommended that we use a 2048-bit key length for our X.509 certificates. Those are the certificates you'd issue from a PKI. So remember, asymmetric comes up in cases where we need to securely transmit a symmetric key for bulk encryption, digital signatures, several other uses, but complementary to symmetric, as I just mentioned. The length of the symmetric key can also affect the security of the cryptographic system, even with a currently accepted algorithm. So you have perfectly secure algorithms that offer differing key lengths. For example, with AES, a 256-bit key length is required in some US government scenarios. AES, for example, supports key lengths of 128, 192, and 256 bits. So shorter key length means fewer possible combinations, which means greater vulnerability to brute force attacks, for example. Next is strength of implementation. So ensuring cryptographic solutions are properly implemented is as important as selection of the secure solutions themselves. It's crucial to implement the systems as recommended and to keep them updated to protect against vulnerabilities. Our next category is misconfiguration, which occurs when a configuration mistake is made, human error, for which impact may vary. There are a variety of ways we can prevent human error. Infrastructure as code, configuration management tools, continuous integration and continuous delivery, or CI/CD, checklists and templates to minimize the need to perform manual steps again and again, change management that requires test and review, and regular security audits and vulnerability scans. All of these will get mentioned somewhere in this series, but all concepts you should be familiar with in terms of their value to security. Moving on to the mobile device category, we have rooting and jailbreaking. Custom firmware downloads are used to root an Android mobile device, for example. This gives us a higher level of permissions on a device and removes some elements of built-in vendor security. The equivalent on Apple's iOS is jailbreaking. It allows you to basically run unauthorized software and to remove device security restrictions. Now you can even still access the Apple App Store, even though jailbreaking has been carried out. For the exam, remember that rooting and jailbreaking remove the vendor restrictions on a mobile device to allow unsupported software to be installed, potentially malicious software to be installed. Continuing with mobile device threats, we have third-party application stores. So there is certainly a danger of downloading apps from third-party app stores, as there is no guarantee of the security of the app being installed. And this is a vulnerability. It poses a risk, as the vetting process for mobile apps in third-party stores may be less rigorous than the official app stores we see for Android and iOS for Apple. And finally, we have sideloading, which enables installing an application package in an APK format, that's an Android format, on a mobile device. It's useful for developers to run trial of third-party apps, but it also allows unauthorized software to be run on a mobile device. And last but not least, the zero-day category. So zero-day exploits are attacks that use a vulnerability that's either unknown to anyone but the attacker or known only to a limited group of people. Basic security practices can often prevent zero-day vulnerabilities. Today, AI, machine learning, and user and entity behavior analysis-driven antivirus, SIM and SOAR, intrusion detection and prevention, extended detection and response, all offer some defense against zero-day exploits because they're not based on watching for signature matches. They're looking for malicious behaviors. They're looking at threat intelligence that helps to identify known bad actors, known malicious IP addresses, software known to contain malware. And here again, all solutions will cover throughout this series. And congratulations, you have reached the end of section 2.3 of the Security Plus Exam Cram Series 2024 edition. I hope you're getting value out of the series. As always, if you have questions, leave me a comment in the comment section below the video. Reach out to me on LinkedIn directly, and I'll look forward to seeing you back here in a couple of days for section 2.4. And until next time, take care and stay safe.